All right, let's just dive right into this explainer. You know that invisible infrastructure that literally powers our entire modern digital world? Yeah, that's what we're talking about today. Every single time you open an app, search for a product, or, frantically refresh a feed when your Wi-Fi drops, you are interacting with some seriously complex data systems. So today we're going to look under the hood of these data-intensive applications and explore the absolute fundamental design principles that keep the whole shebang running smoothly.
But hey, before we try to solve the crazy problems of scale, we probably need to define what exactly makes an application data-intensive in the first place, right? I mean, historically, a lot of software was compute-intensive. The bottleneck was just raw CPU power. But today, for platforms like Twitter, Amazon, or Google, CPU cycles are rarely the limiting factor anymore. Instead, the primary challenges are the massive quantity of data, the extreme complexity of that data, and the relentless, non-stop speed at which it's changing.
So here's our game plan for today. We'll start with the foundation, which is reliability. Then we'll look at growth, tackling the scalability challenge. Next up is the long game, focusing on maintainability. And finally, the synthesis, where we actually build composite architectures. Let's get into it.
Okay, the crucial point here is that engineers rely on a very specific toolkit, these three pillars, to fix basic applications when they inevitably break under pressure. And listen, these aren't just corporate buzzwords. They represent the absolutely critical trade-offs you have to make. Reliability ensures your system survives hardware, software, and human faults. Scalability gives us a concrete way to measure and actually handle increased load. And maintainability? Well, that ensures the system doesn't turn into a total nightmare for the operations team a year down the line. Let's break each of these down.
Chapter 1. The Foundation. Reliability under fire.
So right off the bat, we have to accept a pretty harsh reality. Absolute failure is guaranteed to happen. There's no way around it. We simply cannot reduce the probability of faults to zero. Instead, our job is to build reliable systems from inherently unreliable parts. Now, to do this, we really have to contrast random hardware faults with systematic software errors. Hardware faults, like say a hard drive just dying, are mostly random and uncorrelated. It happens. But software errors? Man, those are terrifying because they are systematic and correlated. Take the infamous 2012 leap second bug. Literally just a tiny software bug in the Linux kernel, right? But it caused countless applications across entirely different servers to hang simultaneously. These kinds of software bugs just lie dormant until some weird, unusual set of circumstances triggers a massive cascading failure.
And here is a totally sobering fact. Despite our absolute best, most advanced technology, human configuration errors actually threaten system reliability far more than network hardware ever will. The stats back this up. Studies show that human operators cause anywhere from 75 to 90% of outages. Compare that to hardware faults, which only account for about 10 to 25%. Mind-blowing, right? So to fix this, we basically have to decouple the places where people make mistakes from the places where they cause actual failures. We do this by giving them fully featured non-production sandbox environments to test their configuration safely.
Moving on to Chapter 2. The growth, the scalability challenge.
Okay, so we've built a rock-solid, reliable base. But what happens if our load literally doubles overnight? Scalability isn't just a simple one-dimensional label. You don't just say a system scales or doesn't scale. It's really about figuring out what options we have for coping with specific types of growth. Let's look at a real-world scenario. Twitter. Back in 2012, they published some completely fascinating data. Users were posting new tweets at a peak rate of about 12,000 writes per second. But the load parameter for users just viewing their home timelines totally dwarfed that. We're talking 300,000 reads per second. Handling 12,000 writes? That's relatively easy. But handling sudden spikes of 300,000 reads, that requires a massive rethink of your architecture. This massive gap forces us to ask what is arguably the ultimate scaling question. How on earth do you deliver messages efficiently when a single user has millions of followers? In the industry, this is known as the fan-out problem. Think about it. If a massive celebrity tweets, that single action triggers millions of database writes if you try to push that tweet to every single follower's timeline simultaneously. It's an absolute nightmare for the system. To survive this scaling load, Twitter literally had to systematically pivot their architecture away from simple querying to a really complex hybrid approach. It's a perfect example of a real-world system failing due to poor initial scaling choices. First, they tried querying a relational database at read time. Honestly, that failed pretty quickly under the immense load. Second attempt? Pushing tweets to individual user caches at write time. Now, this worked great for your average user, but completely broke down when those celebrities tweeted. So ultimately, they moved to a hybrid approach. Average users' tweets are fanned out at write time, but celebrity tweets, those are fetched separately at read time and merged in. And that brilliant little pivot is what prevents the system from collapsing.
And this whole scenario brilliantly illustrates exactly why sudden spikes in traffic load cause such massive delays. Honestly, the easiest way to think of network switch queues is exactly like road traffic congestion. If several nodes decide to send packets to the exact same destination simultaneously, the network switch has to queue them up. It's like cars piling up at a toll booth. If that queue fills up completely, packets are dropped and have to be resent. This queuing effect is, without a doubt, the primary cause of variable, incredibly frustrating network delays.
Which naturally leads us right into the latency trap. When a single web application has to call multiple backend services, it only takes just one, slow backend call to completely ruin the response time for the end user's entire request. Even if only a tiny percentage of backend calls are delayed by queuing, the chance of the end user experiencing a painfully slow load time just skyrockets as you add more backend dependencies to the mix.
So, how do we fix it? To ease these bottlenecks, engineers distribute data using strategies like primary key partitioning. And my absolute favorite analogy for this is an old-fashioned paper encyclopedia. Remember those? Because all the entries are alphabetically sorted by title, you obviously don't have to read all 20 volumes to find the one entry you want. You jump straight to the right book. Partitioning does the exact same thing for our databases. It ensures read requests go straight to the specific node holding the data, bypassing the rest entirely.
Now, evaluating these bottlenecks means engineers are constantly having to trade off between two paths: the superlinear costs of scaling up a single machine versus the incredibly high complexity of scaling out horizontally. Let's break that down. Scaling up, which basically just means buying a bigger, beefier machine, is definitely simpler. But twice the machine size usually costs significantly more than twice the price. It gets expensive fast. Scaling out, on the other hand, distributing your data across a bunch of smaller machines, keeps your costs linear. But man, it introduces massive complexity, especially when you're dealing with stateful data. There's no free lunch here.
Chapter 3. The Long Game. Designing for Maintainability.
All right, to truly survive the complex reality of distributed systems, we really have to look at the human cost of keeping these operations running over time. You know, the vast majority of software costs isn't actually in the initial development. It's in the ongoing, day-to-day maintenance. We have to prioritize operability, simplicity, and evolvability to ensure that our pristine applications don't eventually degrade into a disastrous legacy system, what some engineers lovingly call a big ball of mud. Operability simply means building really good telemetry and monitoring so ops teams aren't fly blind. Simplicity, it means aggressively removing tangled dependencies. And evolvability, or plasticity, well, that ensures that when wild new requirements inevitably come in, the architecture can bend without actually breaking.
And finally, Chapter 4. The Synthesis. Building Composite Architectures.
Let's synthesize everything we've talked about and explore how the extreme requirements of scaling and reliability fundamentally change the very architecture we choose to build. Look, when you're evaluating a system at scale, you'll quickly find that breaking the work down into multiple specialized tools offers massive performance benefits over just relying on a single unified database. Sure, a single database is awesome when you're just starting out, but as load increases, you might suddenly realize you need a dedicated in-memory cache for those lightning-fast reads, a specialized full-text search index for complex queries, and maybe a message queue for all your asynchronous tasks. One size definitely does not fit all anymore.
And this right here is kind of the master key to everything. In a stitched-together composite system, the application code itself essentially serves as the glue to keep those separate message queues, full-text indexes, and memory caches perfectly synced. Because we're no longer relying on that one magical unified database, the application code has to take on the responsibility of orchestrating the entire flow. When your primary database gets updated, the application captures those changes, invalidates the cache, updates the search index, and pushes events right to the message queue. At this point, you really aren't just an application developer anymore. You are a full-blown data system designer stitching together a complex, effective, and resilient architecture.
So, as you head out to design and build your own applications, you face a pretty critical choice. Are you going to take the seemingly easy road and just keep scaling up a single machine until it eventually collapses under the pressure? Or will you embrace the complexity of a composite architecture to truly guarantee your system's reliability, scalability, and maintainability? Think about that. In fact, the next time your absolute favorite app crashes right in the middle of a major event, ask yourself, which choice do you think they made?